Okay guys, so what we're going to do here is we are going to kind of tie everything that we've been talking about together, where we were looking at the first derivative and having it tell us all the things that we needed to know about a function. Then we look at the second derivative and we did the exact same thing. What we're going to be doing here is we're now going to be looking at what the function will actually look like, the original function, based on the fact that we know all of this information about that function now that we can find those things without a calculator. So if I was to look at the function like x to the third minus 6x squared minus 1. If I wanted to look at this function and I wanted to know everything about it, let's kind of go through the different things that we've talked about so far. Like if I have the first derivative, so I had like 3x squared minus 6x, and the second derivative, those can tell us an awful lot of things. Okay, so like, oops, let's see, that's, oh, minus 12x. I knew I was off by something there. Okay, and then that one's 12. So what we've learned so far that the first and second derivative can tell us is where our function's increasing, where our function is decreasing, where we have a relative max, where we have a relative min, where our function is concave up, where our function is concave down, and where it's possible that we have a point of inflection. Now, what we would do if we wanted to is we could say, all right, I need to find where all of those things happen. And the reason why we want to know where all of those things happen is everything that we have found using the first and second derivative is something that will tell us a little bit more about what the original function looks like. In fact, if we put all this information together and we sketch what the original function looks like based on the fact of all of these different things being true, you'll actually get a very accurate representation of what the original function appears to look like. So let's go through all of these things. Now remember, this is like your first derivative, the increasing, decreasing maxes and mins. And the way we found all those things was we took the first derivative and we set it equal to 0. In this case, if I factor out a 3x, I get 3x times x minus 4. And that gives me x equals 0 and 4 as my critical points. Then what I would do is I would make my number line, put both of those on there, so I get 0 and 4. And I look at this and I say, okay, a number smaller than 0, I plug in, we'll go like negative 1. If I plug in negative 1, I get a negative number, times a negative number. That gives me a positive number. And then just in the interest of time, if I chose like 3, I would get a negative number. If I choose a number bigger than 4, like 25, I would get a positive number. Now what that tells me, again, because we're using the first derivative, is that this function is increasing from negative infinity all the way to x equals 0, and it's also increasing from 4 to 25. Or not to 25, excuse me, a positive infinity. I don't know why I wrote 25. All the way to positive infinity. Decreasing, we can see that this function, according to our little number line we just made, is from 0 to 4. And remember, if our derivative changes from a positive sign to a negative sign, the place where that happens, we have a max. And if we change from a negative first derivative value to a positive first derivative value, we have a relative min. So all of that stuff we discovered from using the first derivative. Now, if I was to use the second derivative and do exactly the same thing, remember that tells us some other information because the second derivative tells us about concavity. So I look at this, I've got 2 right there. If I take 0 and plug that into my second derivative, I get a negative number. If I plug in like 40, I get a positive number. So this means my original function is concave up from 2 to infinity and concave down from negative infinity to positive 2, which means at x equals 2, we have a point of inflection. Now, I do realize I went through a lot of that stuff fairly quickly, and I did that because all of this should be a review from what we talked about before. But all of that, now we have all of that information that we can do so we know where those things are happening. But what we're trying to do here, what we're trying to accomplish is we are trying to make it so we know what the original function looks like. So I want to know what the graph is. Now, if I'm looking at a graph, I now know the x values where all these different things occur. But in order to graph something, I need to know an x value and a y value. And so when you're asked for a function value, that is the only time that you actually put a y value down instead of an x value. So in this case, in order to graph this, I need to know the function value that goes with my maximum, my minimum, and my point of inflection. Because if I can get those points onto the graph, then I can say, well, with those points, I know that I can find everything else that I need. I'm trying to erase this stuff up here. Oops. That's not what I want. Okay. I can find everything else that I need just by using those points as kind of a guideline. So for x equals 0, I know I'm going to have a maximum on the graph, but I don't know where to put that dot. So what I would do is I would find f of 0, which is the function value at that point. So I get 0 to the third minus 6 times 0 squared minus 1. So I know the point 0, 1 exists on the function. Okay? Because that is a point. I found that the y value that goes with that x value. And due to the analysis that we did earlier, we know that that value is actually going to be a maximum. Now, and I apologize that I didn't choose a better function to look at, but when I find my minimum, so I get 4 to the third minus 6 times 4 squared minus 1, that's 64 minus 96 minus 1, that gives me negative 33. So the point 4, and again, I apologize. Oh, that's supposed to be negative 1, not positive 1. Dang it. That's negative 1 right there. I apologize. So negative 1 down here. So now I've got the point 4, negative 33, which again, this is not to scale, but this point 4, negative 33 is on the graph. Okay? So I know that that point is a minimum. And then my point of inflection is at x equals 2. So I take 2, plug that in to find out. So I'd get 8 minus 24 minus 1 gives me, let's see, negative 17. That looks about right. Yep. So the point 2, negative 17, again, not to scale, is on my function as well. So I know that those 3 points have to be on my graph. Now from that, what we can say is, all right, I know that this function is increasing from negative infinity all the way to that first point 0. And at the same time, I know that the function is going to be concave down from negative infinity to 0 as well, because we discovered that using the second derivative. So I would draw an increasing concave down function till that point. Then from 0 to 2, notice I'm decreasing from 0 to 4, but from 0 to 2, my function is concave down, so it would continue to be a frowny face until that point. Then from 2 to 4, notice I am concave up, but I am still decreasing, so my function would kind of come down like that, and it would be a lot smoother than the way I've drawn it, but that would look like that. Then from 4 on, I would be both concave up and increasing. Both of those things at the same time would be true. So my function would look something like that. Now, if you were to actually graph this on a calculator and you were able to make the window so it was to scale, you would be shocked at how accurate this is as a representation of what the function actually looks like. And so that's why this is so nice. This curve sketching, you can get a really accurate representation just by using these techniques we learned with the first and the second derivative. So here's another one. What I'm going to do is I'm going to pause the movie for just a second, solve this real quick, and then you can check to see if your graph looks the same as this one. So give me just a second, and the answers will pop up here in just a sec.